Hey, are you alone? Are you sure? Okay, good. Because I've got a secret. Hi. Please don't hate me because of what I'm going to tell you. We're friends, right? Friends? Okay, here it goes. I don't believe that stacking subframes increases signal. Welcome to Deep Sky Detail. For some of you, this might be obvious. For others, you might be surprised as to why I don't think stacking increases signal. Let me be clear, stacking is great, stacking is good, stacking works. I love stacking. But stacking, the way most of us do it, doesn't increase signal, and I think it's important to understand why, because knowing this can get you better images. Now I know what some of you are telling yourself right now. The more images I stack, the more I can stretch the image and make it brighter. Stacking must increase signal. To that I would say, repeat what you just said. The more you stack, the more you can stretch the image. You are stretching the image. You're using software to make the image brighter. The image itself doesn't get brighter by simply stacking. Stacking smooths out the signal. It makes the signal stable. It averages it. At the same time, stacking gets rid of noise. The elimination of noise makes stretching worth it. And this is where the confusion comes in. The whole conversation is very nuanced. Craig Stark, the original developer of PhD Guiding and my hero, gave a presentation that is on OPT's YouTube channel. I'll link it in the description. It's all about signal and noise. In the presentation, Craig Stark says that stacking increases signal, but he also said this.
So, how do we do things like boost our signal? Well, one thing that you can do, and we can debate whether this is truly boosting signal or actually reducing noise, but one thing that we can do is we can, well, just stack more images. We can debate whether this is truly boosting signal or actually reducing noise.
Now, why did he say we can debate whether stacking increases signal or decreases noise? Why? Stacking makes it easier to bring out the signal, but it does so by decreasing the noise. To this argument, I'm going to offer 3 pieces of evidence, an increasing complexity. The first is purely visual. The second is based on real-world signal-to-noise ratio calculations presented as a graph, and the third is based on the math obtaining a signal-to-noise ratio. Before I get into all the evidence though, let's first define a few things. Signal in astrophotography is just measuring photons hitting your camera's sensor from the deep sky object you are imaging. The rest is just noise. The sky globe background is noise. Your camera's read noise is noise. But the main thing to remember is this. Signal comes from the deep sky object itself. It's what we're interested in. Okay, so let's get to point number 1. Let's take a look at these 2 stacked images. One is about 1,000 15-second light frames, and the other is about 2,700 15-second light frames. Neither one is stretched. Can you tell the difference between the 2 images' brightness? Neither can I. This is one thing that I think bothers a lot of beginners. They take several light frames and stack them. But the resulting stacked image in Deep Sky Stacker or Serial or whatever is always just really dark. If we do a simple auto stretch on them though, we can start to see the difference. The 2700 stacked image has a lot less noise, but the brightness is really similar. Point number 2 is taken from real-world data. In my last video I talked about how I computed the signal-to-noise ratio of 1700 subframes. I could do this for individual pixels. The last video might be helpful in understanding all of this, so go ahead and check it out after watching this video. Basically, to calculate the signal-to-noise ratio of a pixel, I just need to know the signal of the pixel and the noise of the pixel. I can graph that. The x-axis represents the number of stacked frames, and the y-axis represents the signal of the pixel from each stack. As you can see, when few subframes are stacked, the signal is sort of all over the place for the pixel. But as we stack more and more subframes, the signal stabilizes. It flattens out. It doesn't go up, it doesn't go down. It flattens out. But why does it get easier to stretch images with more frames then? Well, the answer has to do with the noise. We can also plot that. The noise decreases as we stack. At first it decreases a lot, but after a while the rate of decrease diminishes, but it will generally always decrease with more stacked images. Stretching gets easier because the noise keeps getting smaller, allowing the signal to shine through. That's what the signal to noise ratio tells us after all. Okay, point number 3 is just a simple mathematical explanation of the signal to noise ratio, or SNR. This is a bit more math-based, but it is essentially the same thing I plotted in point number 2. Signal is the measured photons from our deep space object hitting the sensor. When stacking, signal becomes the average number of photons of our DSO object hitting the sensor each light frame. This is the numerator of the SNR measurement. The denominator of the SNR measurement is the noise. When stacking, the noise is the square root of all the sources of electrons being recorded in our sensor, divided by the number of stacked images. So if there are electrons from the sky background, they get added to the electrons from the dark current. Those are added to the electrons recorded from our deep sky object. We can then take the signal and divide by the noise to get the signal to noise ratio. I know what some of you who are mathematically inclined are already thinking. You might say, hey, the noise measurement is a fraction. We can add the number of stacked frames of the noise measurement to the numerator of the SNR measurement. The numerator of the SNR measurement is then the signal times the number of stacked frames. Signal increases with stacking. The numerator of the SNR measurement is then the signal times the square root of the number of stacked frames. Signal increases with stacking. To that I would say no. What you have done is transformed the SNR calculation. The signal to noise ratio increases with stacking, not the signal. Remember, we have already defined the signal as the average number of photons hitting your camera sensor from the deep sky object you're imaging. If signal increases with stacking, the pixels and resulting image should get brighter as the number of images you stack increases, but that doesn't happen. So what's the conclusion? Stacking increases the signal to noise ratio. It does not increase the signal. And at this point, some of you may be wondering, why is this even important? Why should I care? Well, I think that there's a bit of a misconception in astrophotography, that as long as you gather enough data, you can bring out any detail from any object that you want. It's sort of a, my signal will keep getting better kind of mentality. This mentality sometimes isn't all that practical though. If your signal doesn't beat your noise by a large enough margin, you may need to image for thousands of hours to get a good SNR ratio. And even then, it might not be enough to get a satisfactory image. Let me give you an example. When I first released my signal to noise ratio app, I got some feedback from a user who was imaging without any filters in the Bortle 2 zone. Sounds pretty good, right? The user was trying to image an extremely faint emission nebula. With a great camera, they needed around 900 hours to get a decent SNR of 75 with 3-minute exposures. I don't know about you, but I'm not sure if I even have 900 hours of clear skies a year. The signal from 180-second subscribers, subframes, without a filter is just not strong enough to outweigh even the faint sky glow of a Bortle 2 zone. Stacking alone isn't going to cut it, even under pristine skies. In this case, getting rid of the faint sky glow background with a filter would help a lot. Also, longer exposures would help because there is so little light pollution. Normally, light pollution makes sub-exposure length irrelevant because the sky pollution noise increases at the same rate as the deep sky object target signal. But if you have dark skies, then increasing exposure length can really make the signal punch through the noise a lot more quickly. Whew. Well, as you can see, I've thought way too much about signal and noise for way too long. I think I'll end it here. Check out my other videos if you haven't already, and thanks for watching.